Hi, everyone. So my name is Christophe Corre. I will be giving this talk, which is a joint work with Dominique Schuster, Ince, and Alexis Giauque at Fluid Mechanics and Acoustics Lab in Ecole Centrale de Lyon, and which is this work is devoted to the assessment of.
Christophe, could you speak just a little bit? It's a little quiet on our side. We'll try to get the mic closer to you, but.
No problem, no problem. So this work will be devoted to the assessment of some compressibility corrections for RANS simulation of perfect and real gas flows using, obviously, SU2. Next slide, please. So I will briefly mention the context and motivation of the work. Then I will focus on some density corrections which were recently proposed. I will show a few results obtained for the compressible boundary layer on flat plates, and I will give the numerous perspectives of this work. Next slide, please. So what's the motivation for this work? Well, as you all know, the laws which are applied for the derivation and calibration of turbulence models, they do not actually guarantee their relevance for high-speed flows because they are basically incompressible flow laws. And turbulence closure generally neglects pressure dilatation, dilatational dissipation, so that compressibility effects are not properly accounted for. Still, we know that experiments show that such effects, even at moderate Mach numbers, can be significant. And we have examples in mind with the compressible mixing layer, which is a very well-known example of strong impact of compressibility effect on the spreading rate of the mixing layer. We have also in mind the reduction of skin fraction when you increase the free stream Mach number for a compressible boundary layer. Next slide, please. So regarding how to properly take into account compressibility or density effects in a turbulence model, we have, of course, the seminal works by Sarkar and by Zeman, which at the time were focused on the K epsilon model. The key idea was actually to modify the dissipation in the K equation. And this was shown to bring significant improvement for the compressible mixing layer, but not really for a compressible boundary layer, actually. This motivated also the following work by Wilcox in 1992 with modified dissipation, which was found to ensure both a good prediction for mixing layer, compressible boundary layer, but not for a shock-induced separation in a compression corner, for instance. Next slide, please. Regarding the Spallart-Almaraz model, compressibility correction was proposed back in 1995. It's called a Segondov correction, and it's a contribution which is added in the dissipation term of the modified viscosity equation. And again, this was shown to bring significant improvement for the compressible mixing layer prediction. You have other approaches, for instance, Paciori and Sabeta in 2003 proposed a reduction of the production term, which was again proved to improve the compressible mixing layer prediction. The correction was actually tailored for this case, but which was found to degrade actually the prediction for overflow configurations such as compressible boundary layer. Next slide, please. So apart from this first series of compressibility correction, you have also density correction, which were proposed initially by Catrice and Opois in 2000. And basically, the idea was actually that you need to modify the diffusion terms in be it one or two equation turbulence model so that you make them consistent with the logarithmic law for compressible boundary layers. This same idea was also explored more recently in 2018 by a group of Pechnik at the TU Delft using a different strategy and leading to similar or analogous density correction for the diffusion terms of common RANS model, including Spallart and K omega SST. Next slide, please. So the tasks and objectives of the present contribution are the following one. First, we want to implement in SU2 this Pechnik and Al density correction, as well as compressibility correction from the literature for K omega SST. Segondov correction is actually already available and implemented in SU2. We want, of course, to assess these corrections for a number of test cases. As I have tried to emphasize in this quick introduction and review of the literature, you really need actually to cover a variety of test cases in order to fully assess the potential of your correction and their effects. So, of course, boundary layer, but also mixing layer, shock boundary layer interactions, such as the nice results that we've seen in the previous talk, and eventually turbine configuration, typically an ORC turbine configuration in our case, which displays these various flow features. So our objective is to perform this analysis both for ideal gas flows, and when you look at Spalart-Almaraz model, for instance, you have similar work which was performed by Serrer and Kosarev in 2017, for instance, and of course also real gas flows, and more specifically dense gases. So this is a teamwork which is in progress, because this is a number of test cases to compute. And today I will only present some preliminary results obtained for a compressible boundary layer using SA, using K-omega SFT, and Pechnik et al. Density corrections. Next slide, please. Thanks. So this density correction, what do they look like? The idea is, if you look at Formula 1, you've got on the left-hand side, you've got the typical expression of the diffusion term in the K and in the omega equation, which we all well know. And the idea is that to properly account for density variation, and again to properly recover the law of the wall and the log law for compressible boundary layers, you should actually introduce density terms in the diffusion according to the formula which are given here on the right-hand side. So I'm not going to detail where all this comes from. I'm going to focus on the implementation in SU2. So the idea was actually to implement this correction in the form of existing terms coded already in SU2, plus some corrections depending on the density gradient, and also because, of course, we want to preserve as much as possible conservative formulation. Also, we want to use only the gradient of K and omega, not the gradient of rho K, for instance, because we know that those are the gradients which are already available. Next slide, please. So the idea is that with this in mind, you can expand, it's a little calculus, really basic. You can actually expand the Pechnik formulation in the following form, where you recover the, in black, I would say the baseline term, okay? Plus in blue, it's a new term, which is in the form of a diffusion term, which depends, as you see, on a density gradient, plus some extra terms, which are here in red, which take the form of source terms and which you will need to code as source term. And you proceed similarly for the modified diffusion term for the specific, for omega, specific dissipation. Next slide, please. So for the K-omega SST model and to finish on the implementation, of course, you need to take into account the fact that you deal with a finite volume solver. So here I'm just writing the integral form of the conservation laws we need to solve. And what you see is that, of course, the blue terms are just giving you a new contribution to the diffusive flux, and the red terms give you new source terms which you need to compute. So it's a straightforward space discretization. It's quite easy to implement in SU2. It uses mostly available quantities. Of course, you have new terms to compute, in particular the projected density gradient, grad rho, which must be computed, but you just need to apply the same procedure as the one used for computing the projected gradient of K and omega. Next slide, please. So for Spalart-Almaraz, you've got here again Formula 6, the proposal made by Pechnik et al. Of the modification. So you've got the modification of the diffusion term and a modification of the cross diffusion term. And again, the idea is going to be the same. You're going to express a modified diffusion as the baseline term, which is available, coded, implemented in SU2, plus a new flux term in blue, plus a new source term in red, and the modified cross diffusion, which is already a source term. You have an added two actually added source terms which you need to compute. Okay, so this has been oh, and I think I have on the next slide, please. Just as a reminder, of course, the finite volume formulation to distinguish clearly between the flux term in blue and the extra source terms which you need to code. And again, the space discretization is straightforward. So this has been implemented in SU2, and we can go to the next slide. And we are just going to present some results obtained for the compressible flat plate boundary layer. It's a boundary layer at characteristic Reynolds number 5 million. Computational refinement, it's such that you ensure grid convergence for all flow configuration, second order space discretization. And we will mostly compare the results with the theory, and in particular the log law with, of course, boundaries transform velocity. Next slide, please. So here, just to be sure, we computed, of course, this is in the tutorial of SU2. Actually, we just recomputed, of course, the low Mach number, so quasi incompressible case, and we see that we have something perfectly nice for Spallart. This is a baseline model. And we can see we have something nice for K omega with maybe a behavior which is not necessarily what we were expecting in the buffer layer, but this will need to be investigated in another context. Next slide, please. So now we are increasing the Mach number, and we are dealing with Mach 2, Mach 3.25 on the left plot using a Spallart-Almaraz baseline model, and using SST, Mach 2 and Mach 4 on the right plot. And what we can see is that actually with Spallart, this was a bit expected from the literature, we don't have that much impact, I would say. With K omega SST, it's quite clear that at Mach 4, with this baseline model, you actually tend to lose the proper prediction of the log law. So next slide, please. Just a quick word before showing, of course, the impact of the corrected model. When you increase the Mach number, your log law region actually tends to decrease. Okay, so we're going to focus on what's going on between a few tens and just 100, 200, no more for y plus coordinate. And even though the extent is reduced, still the RANS model should correctly reproduce this log law, as we will see also with a comparison with the experiment in the next slide. So we can move to the next slide. And now here, thanks, we see the comparison with the baseline and the modified model for the 3.25 computation on the left with Spallart and Mach 4 computation on the right with SST. So with Spallart, we really don't see much difference. We have analyzed this with the contribution of the terms, but I'm not showing details here for lack of time. On the right, what's interesting is that we see, even though you need a bit of believer's eyes, but still, we see that we have a slight improvement in the log law prediction for the K omega SST model when we apply the density correction. And we see when we look at the contribution of the terms, comparing this green modified curve and the blue baseline curve, we see that indeed there's a contribution of the correction in this region where we want to recover the log law. So moving to the next slide, please.
Yeah. 2 minutes left.
Yes, no problem. I should be on time. Thanks a lot. We just make also a comparison for the Mach 4 calculation with available experiments, which are in red here. So it's the same curve as the previous one, but you have on top of that the red curve. So we see that there's something probably which need to be fixed with the K omega SST for the buffer layer, but this has nothing to do with density correction because it's already there for the baseline model. And we see that the experiment is in good agreement also with the theoretical log law. So the green curve, I would say, is indeed a better match than the blue one. Next slide, please. We've done also some, started to do a real gas simulation, because this is, of course, a topic which is of particular interest for us. We work with the same Reynolds number. We've adjusted the length of the plate to preserve 5 million. And here I'm showing the results obtained both with the baseline models and the modified version. And what we see for 3.25 or 4, and what we see is that actually we have only limited compressibility effects for this dense gas boundary layer, so that there's no significant effect of the density correction on the result. Next slide, please. So the perspectives of the work. They are numerous, okay, but I'm going to summarize them in 3 slides, short. First, from a numerical viewpoint, I'm just showing here that all the results, they are correctly converged, okay? So what I showed has been checked to be steady state. Still, you see on the right that when you start having the modified model which acts on the solution, it has an impact on the proper convergence, really to zero machine steady state, okay? You converge to a steady state, but the convergence is not as smooth as for the baseline model. And this, we know perfectly why. It's because we need to take into account the density correction into the implicit stage, which we have not yet done. Okay, so this has to be implemented. We know to do it, but we need to code it. Next slide, please. Of course, we need to pursue the physical analysis. What has been shown is preliminary. We need to complete for the boundary layer with splint friction assessment, obviously. We want to focus on compressible mixing layer, especially because we have a number of DNS results for the compressible mixing layer in perfect, but also in real gas. Okay, so we see with a lot of interest what is the impact, and this is what we are currently computing, of this compressibility correction for the compressible mixing layer, for shock boundary layer interaction as well. And if we can have exchanges with a previous speaker, it will be with pleasure. And on the last slide, please. Our final targeted configuration is the annular cascade, which was experimentally studied by Otter for air, for real gas as well. And we are currently computing these flows with the baseline model. We are going to compute it with the modified models. And of course, as you can notice, we are curious to see what will be the impact of the density compressibility correction, because we have in particular a key interaction between the trailing edge oblique shock and the boundary layer developing on the section side of the blade. And this concludes my talk. Thank you very much.
Thank you very much, Christophe, for the talk. Very well, we are left with 3 minutes for questions. Anyone from the audience? Anyone? Okay, yeah, please go.
Yeah, I have one for you, Christophe. So in my experience, adding more terms in the source terms and messing around with source terms of the turbulence models causes a lot of numerical issues. So if you guys had to do anything with clipping or any numerical fixes, I know you talked about the implicit addition you need to make, but are there any other interesting things you found?
For the time being, my experience with, I fully agree with you, even though the sound was not very good, but I think I heard your question. I think I fully agree with the fact that there's a sensitivity to the source term. Okay, so when you modify the source term, you should expect some numerical impact. My experience is also that dealing properly with a bit of implicitation, proper implicitation of the source term contributing to the dominant diagonal term, most of the time, as far as I can see, it stabilizes the simulation. And up to now, apart from this lack of convergence, okay, full convergence, not preventing proper analysis of the solution, we have not had too many numerical issues. So we are maybe wrongly. We are confident that we dealing with source term in an implicit way should hopefully be enough.
Sounds good. Thanks.